Okay, so we're going to talk a little bit about the shell, or the orbital, electron orbital. What is this electron orbital? Are you asking me? No, I'm just thinking myself a little bit, taking a little bit extra time. So the electron orbital is the region where electron resides. And so we still kind of keep this idea that an electron can be identified as a particle. It does have mass, and we can measure its mass and measure its momentum, and that's different than light. Light, generally, we don't think of it as having momentum because we don't record it as having mass. But electrons do have mass, and so we can also kind of identify their location. But in general, the wave function, which is an equation which will tell us the shape of the electron cloud, just basically is telling us the probability or a density map of the likelihood of an electron being in a given location. Kind of like this s orbital here, it represents, with these little blue spots, basically the probability of the electron being in a given location. Also, you could think about it as the distance of the probability of an electron residing a given distance from the nucleus. The likelihood is that they'll be close, but they can also be kind of far away. But again, this isn't the model that gives us the information about the transition energy, right? In general, this is one three-dimensional electromagnetic wave function, just one potential of energy. The s orbitals are spherical, like we mentioned, but they do have nodes inside them. Remember that speaker that we saw vibrating and the sand going all over the place? You could see the nodes, or the region where there was no density. The same thing occurs in our three-dimensional models. Our p orbitals also have nodes. We saw that already, so we're not going to, well, we could see it again for those of you who forgot. But essentially what we see here is when we shake when our surface, our speaker vibrates, the salt moves to spaces where there's no vibration, and that helps us identify those nodes. And within shells, within subshells, there are also regions of no electron density. Okay, these are the shapes of our p orbitals. P orbitals, dumbbell shaped. They go along the px, py, or pz. They go on the xy or z axis, and they're labeled px or py or pz. Okay, these are the shape of the d orbitals. We told you that we would show you these, and so here they are. Is that two d orbitals? Nope, this is just one. One right here, second, third, fourth, and fifth. Okay, crazy looking, huh? Yeah. All right, so what that does for us now is it helps us kind of get a spatial orientation of our orbitals. I also have another kind of cartoon to help us think about the atom. Just a second. Okay, so here I have kind of a diagram to help us think about our 1s orbital. This little thing right here in the middle is our nucleus. So we have our nucleus, and here I have one electron kind of zooming around in this orbital. So what this is doing is trying to mesh our old model with our new model to help us kind of visualize it in our mind. This is the 1s orbital. It holds 2 electrons, right? And after we fill the 1s orbital, we need to bring in our second shell. And our second shell has 2 subshells, the 2s and the 2p subshells. Okay, here's our coordinate to help us kind of spatially position ourselves. Our 2p's, our p orbitals, right? 2p subshells are along our x, y, and z axis. Our 2s orbital holds 2 electrons. And then, as we continue to put more electrons in, the next electrons go into our 2p. We get 1 into each of those 2p subshells, or 2p orbitals. And then after each one has 2 electrons, our 2p subshell is full. Okay, so backing out a little bit to have a little more space. So there's our first shell. Here's our second shell that we talked about already. And now we're bringing in our third shell, which consists of a 3s, a 3p, and a 3d subshell. All right. So it doesn't help to kind of continue this model any further because it gets too confusing to see what's going on. But hopefully you can see how the layering of these shells, how each shell contains subshells, and the spatial orientation of the electrons. Hopefully that helped you kind of visualize what's going on a little bit. Okay, so there's something that happens to electrons that are on the outer edge of an atom. All right, they get shielded from the from the nucleus, the protons in the nucleus, so they don't feel as much of that attractive nuclear charge. The effective nuclear charge is what we say is the amount of attraction that our outer electrons have because of the positive protons in the middle. And because of this shielding that occurs, as you add electrons, then you can, as you add electrons to an atom, the electrons that are added get farther and farther away, and they become a little bit easier to perform chemistry on, or to be removed, or to interact with other atoms, right? So this shielding is something that we have to be aware of, and the effective nuclear charge due to the shielding is also something we have to be aware of, okay? And because of these principles, we get certain trends in terms of size of atoms along the periodic table, all right? Moving down, as you get into outer shells, there's less of an effective nuclear charge, and so the atoms become larger, all right? So lithium, electron configuration of 1s2, 2s1, right, has a size of 152 picometers, that's the radius there. And sodium is larger size, 186, because its electrons are in a 3s1, its outer electrons in a 3s1 orbital, and that is feeling less of an effective nuclear charge because of the electrons which are below it. And so as you get more and more electrons, the atoms get larger. However, if you look at within subshells, like going from 3s1 to 3s2, you're putting an additional electron in, but the atom is actually shrinking. See the same trend across our 2p, sorry, this is our 3p. 3p electrons going from aluminum to argon, the elements actually get smaller as electrons go in. Now, why is this the case? If I had showed you this to you early on and said, look at this, see why atoms behave this way, or see that atoms behave this way, we'd have no foundation for understanding why it was. Our old model would have suggested that as we fill in electrons, the atom should get larger and larger and larger. But what this is showing is that as you fill in those subshells, because they're the same subshell, they're the same distance from the nucleus, that the atoms don't get larger. In fact, they get smaller simply because there's an increase in the effective nuclear charge. Or in other words, there's more protons. Every time you move to the right in the periodic table, you're getting more protons, right? Okay. Another trend that we'd like to pay attention to here is the trend for the ions. Here is a sodium atom, and here's its ion. Why is the ion so much smaller? That's a good question. The ion is so much smaller because it's lost that outer electron, but it hasn't lost any protons. And so all the other electrons get a little more attention and can shrink down. Okay? I like to use this analogy of going to the mall with my kids. When I go to the mall, usually it's me and my wife. So here I am. Here's my wife, right? We're at the mall, and we're walking along, and we have our children, right? Now, the children don't walk as orderly as we do. We always hold hands, and we're always right next to each other and walking straight, very nice and neat. But the kids, they roam, right? They are always just wandering around. So we walk down our hallway of the mall, and the kids, these represent the kids, right? They are just walking around all over the place. And it makes our family's size a little bit bigger, right? Now, the parents in the middle, like the nucleus, is always telling the kids, hey, come back, settle down, come closer, come closer. And so our effective nuclear charge is drawing the children closer. But they will continually try to stray and come out to the edges, all right? But what happens if you go to the mall with one less children? Or if one child moves out, then what happens? It decreases significantly the size, because now each child gets more attention from the parents and tells the children to come back in. Same thing when you go to an atom, from an atom to its cation or lose an electron. Now all the electrons get a little more attention, and the size of the ion is smaller than the atom. However, if you do the same thing, if you say, oh, can our neighbor friend come? Well, that neighbor friend's not going to get nearly as much attention, and we're going to take up a much larger swath in the mall. Okay? All the kids get a little less attention, the neighbor kid gets less attention, and so we take up a larger swath. And that's what we see as well when we go from, for example, the chloride ion or atom to the chloride ion.
The ion's a lot bigger?
That's right. The ion's a lot bigger because that extra electron doesn't get as much attention. Its effective nuclear charge is smaller. So cations are smaller than their atoms, whereas anions are larger than their atoms. Does that make sense?
Yeah, I get that.
Okay, so which of the following correctly compares the sizes of the entities?
Oxygen should not be... The ion should be larger, so that's not right. Neon and magnesium. Can you give me the periodic table? Neon.
Here's magnesium. Here's neon over here.
Neon would be smaller simply because its electrons are not in the third shell. Is that right? Did I say that right?
Let's see. Here's the neon. It's the second shell. Magnesium has electrons in the third shell. Good.
Magnesium metal would be... That's right. Just the atom is larger than the ion because the ion loses 2 electrons.
Very good. Excellent job. Okay. As we said, positive ions are always smaller. Negative ions are always larger. Okay. Good place to stop.